Welcome to the demonstration featuring the iWave Versal AI Edge DevKit platform integrated with the Analog Devices AD FMC OMMS3EBZ FMC module. Together, they deliver high performance, low latency, and power efficiency, enabling advanced RF signal processing, software-defined radio, and next-generation wireless communication. The iWave Rainbow WG57M system on module is ideal for applications such as LiDAR, radar, robotics, surveillance, and medical imaging, accelerating development while reducing risk and complexity. The AD-FMC OMMS3EBZ is a versatile SDR module based on the AD9361 RF transceiver, supporting frequencies from 70 MHz to 6 GHz, MIMO capability, and configurable bandwidths up to 56 MHz. Making it a perfect match for FPGA-based platforms via FMC connectors. The diagram below provides a high-level block representation of the system. In this setup, the FMC module connects to iWave's development platform, which supports both Versal AI Edge and Zynq UltraScale plus MPSoC devices. The development platform is powered by a 12-volt, 5-ampere power supply and features a USB Type-C UART interface for accessing the board console. The ADI-IO oscilloscope tool can be connected to the platform via the Ethernet port for real-time RF data visualization and analysis. It supports high-speed connectivity through the FMC Plus connector, which includes GTP transceivers and LVDS single-ended I/O signals. Now, we connect the AD-FMC OMMS3EBZ FMC module to the FMC Plus connector on iWave's development platform. Using SMA connectors, we link the signal generator, connect the analog input signal from the signal generator to the RX1A port. The processed output from the TX1A port is looped back to the RX2A port. Finally, the TX2A port is connected to a spectrum analyzer to analyze the transmitted signal. Power up the development platform and open the terminal or minicom to access the debug UART port. Wait for the debug prints to appear, confirming that the system has successfully booted and is ready for operation. Configure the Ethernet interface and assign the IP address to enable access to the development kit over a wired network. Now identify the I/O device number assigned to the AD9361 transceiver. Navigate to the AD9361 I/O device directory using the following command. Set the RX and TX LO frequencies to match the signal generated by the signal generator. To configure the RF operating mode, navigate to the debug directory and enable loopback mode using the following commands. Connect a storage device, such as a USB pen drive, to the development board to capture real-time ADC data. After capturing the data, unmount the storage device, then connect to the host PC and copy the data. Using the Octave tool, you can load the captured data and visualize it in 3 modes: time domain, frequency domain, and constellation plot, and analyze the waveform. Alternatively, you can use the ADI-IO oscilloscope tool to visualize the captured data in 4 different modes: time domain, frequency domain, constellation, and cross-correlation. The tool also provides access to various RF parameters and settings for real-time monitoring and configuration. To use the I/O oscilloscope, ensure that both the development board and the host PC are connected to the same Ethernet network. The development platform is also compatible with iWave's Zynq UltraScale plus MPSoC based system on modules, SOMs. iWave Zynq UltraScale plus MPSoC ZU5 EV system on module, a compact, high-performance solution designed for edge computing and embedded processing. This module comes equipped with 2 GB of dedicated FPGA DDR4 memory and 16 GB of onboard eMMC flash. Now, replace iWave's Versal AI Edge SOM with iWave's Zynq UltraScale plus MPSoC SOM. Once the new module is connected to the development platform, simply follow the same steps to capture ADC data using the Zynq UltraScale Plus platform.